Okay. Okay. So the only thing I talked about was some stories. So let's start here. So what is algebraic geometry? So there are two aspects to algebraic geometry. Yeah. So there is algebra and then there is geometry. So there are two parts to it, and sort of algebraic geometry is when you think of them as same in some sense. Yeah. So what is algebra? So what do we understand about from algebra? What is algebra about? So what do we study when we think about algebra? Yeah. So I mean, so if you are in high school, then you would say algebra is about solving equations, solving some equations like quadratic equations, cubic equations, and so on, involving polynomials. So this is or maybe polynomial and so on. Yeah. So this is what algebra is when you haven't entered college, and then when you enter college, it's groups, rings, fields. And so on, modules, etc. Okay, so modules as well. Modules. So this is algebra. What about geometry? So geometry. I mean, naively speaking, geometry is about pictures and so on. So pictures. So I mean, in high school there isn't much. I mean, okay, maybe some geometry we see. Yeah, like so. But those are, I mean, mostly we see plane geometry, but that's not related. I mean, that's not going to be the center. But let me just put it here, geometry. But we also see, for instance, you in 11th, 12th at least, you see something called coordinate geometry. Yeah, so that is more in line with algebraic geometry. Some first few instances of algebraic geometry. So what was called, at least in my days, it was called coordinate geometry. I don't know these days. Things may have, terminology may have changed. So for instance, so what do we study in our coordinate geometry? So we study like loci of some equations, yeah. So like a circle, ellipse, etc. Circle, parabola. Okay. So so now what is the connection? So obviously there is a connection, right? So and okay, so part 2 I haven't written because part 2 I don't know, it hasn't been covered at least in BMath. So or maybe some part is covered, yeah. So you must have seen manifolds. So
yeah, we have seen.
Yeah, because of this curves and surfaces.
Geometry. Yeah.
So manifolds is that sort of geometry, and then we will talk about in this course we will talk about varieties. So when you go to college, you as you see, I mean, algebra becomes about group, rings, fields, modules, etc. And hopefully you know why polynomials come into picture in all this. And then geometry becomes a topic of becomes about manifolds, varieties, and of course schemes, etc. as well. And there is some topology. So topology is a way to study all of them. So topology comes in somehow. So maybe I'll just put topology is sort of like geometry. Yeah. So okay. So maybe. So what is the connection? So algebra on one side and geometry on one side. Yeah. So geometry. So of course, when I have to explain someone what I work on, the first example I give is this one. So I say it's algebraic geometry, and what is algebraic geometry about? Is about. So it's about. So on one hand, you have x square plus y square equals 1. So this is algebra. But of course, as soon as you give this equation, a good number of people think of a circle. Yeah. So it's both algebra and geometry. So you get so you can study circle using this algebra equation, or you can study this algebra equation using the circle. And so there is no distinction between them in some sense. Yeah? And that is what algebraic geometry is, studying geometry using algebraic methods, or studying algebra using geometric methods. What depends upon what interests you, or what are the questions involved. And then, of course, circle is one example, and then you can take a more complicated example. So somehow we will, so maybe I'll write this example, and later on I'll say why this is slightly different from the previous one. So if you think about this, this is another example of, so instead of that equation, this is a slightly more complicated equation. Yeah, it has degree 3 in x, degree 2 in y. This has degree, this is a degree 2 equation, and the second one is a degree 3 equation. So its graph also looks very different. So I have a, so it's symmetric about y-axis. So x is 0, x is 1, and x is 2. So it intersects at these 3 points. And so I'm drawing a real picture. Yeah. So x, y, z, you think x, y, you think of it as real numbers. So x could be more positive or negative, and y will be square. Sorry, y could be. So you want to make sure that this, so since y square is always positive, you want to make sure that this is always positive. Yeah. So you have to figure out where it is always positive. So if you take x less than 0, it's always negative. So you can't take x less than 0. It has to be between, so you can, it has to, but between 0 and 1, if x is between 0 and 1, then you can see that it is positive. So you get 2 values of y, except at 0 and 1, where you get only 1 value. And then again, if you are between 1 and 2, then you get, then this right-hand side becomes negative. Okay, so you don't get anything, but once you go past 2, then all the 3 terms are positive, and you get a picture like something like this. Okay, sort of diverges. So I'm not good at drawing pictures. So asymptotes, there are no asymptotes. Yeah. So it may look like I'm drawing an asymptote somewhere here, but it goes to infinity. So sort of, yeah, not really an asymptote. So this is how it looks like. So this is so in algebraic geometry, this is part of P1 projective line, which we'll talk about, and this is also, this is part of what is called an elliptic curve. So there's part, meaning it's a big part of it. Yeah. So there's only 1 or 2 points missing. Not too many things missing. So so this is how and they are different in the sense that, I mean, pictorially you can see they are different. Equations also you can see they are different, and so you can when you study anything, one of the objective is to classify them. Yeah. So for instance, if you study groups, you want to classify all finite groups. Yeah. And then people have written some 1,000-page paper to classify at some finite simple groups. Yeah. So similarly, rings, etc. You want to do some sort of classification up to when you put some restrictions on them, you want to classify. So similarly, in algebraic geometry as well, there are these geometric objects, and you want to classify them. So, so for instance, you would want to classify these pictures I have drawn, curves, so to speak, and surfaces. So one-dimensional object, two-dimensional object, three-dimensional object, all geometric objects. Yeah. So there has been reasonable success for one-dimensional object. There has been some success, and two-dimensional object as well. There has been some success. Three-dimensional onwards is all open. Yeah, so it's a fairly open area to work on, algebraic geometry. Almost, I mean, in the sense of classification. So classification is one of the problem. So that's fairly open, and then there are many. It's one of the hottest area in mathematics. So there are many open problems, many things people talk about, and so on. Okay, so this is translating high school algebra to geometry, but of course. We will, so in this course, we will see how to connect this algebra, groups, rings, so mostly rings to geometry. So so maybe how do you connect this high school algebra to high university algebra, so to speak? So you consider this kxy or rxy in this ring, rxy. So and think of this ideal x square plus y square minus 1. Yeah. So this is some ring. Yeah. So it consists of. So if you just think of rxy, these are polynomials. Yeah. And when you go mod this ideals, these are equivalence classes of polynomials. Yeah. So polynomials, of course, you can think of them as functions. And so even equivalence class of, so if you take a polynomial in rxy, this is going to be a function in two variables. Yeah. But if you go mod this x square plus y square minus 1, so then that means two polynomials may be, these two functions might be equivalent. So equivalent where? So I mean, if you evaluate it at on this circle, any two polynomial in the same equivalence class, then you'll get the same value, because on the circle x square plus y square is 1. Yeah. So we make we cook up these rings, and these gives you functions on your geometric objects. So like in manifold, you study functions on your manifolds. Yeah, you just don't study the shape. So just studying the shape is topology, but when you go to geometry, then you sort of study functions on them as well. So that's where these rings come in. So these rings are basically functions on the corresponding geometric object. Okay. So maybe so maybe since I made this comment, let me just show you an example. Yeah. So and this rings. So there are other parts of it as well, but let me just make this using an example. Yeah. So for instance, you take two functions here in Rxy. So maybe x is one function. Yeah. So fx equals x. So fx equals x is one function on this whole plane. Since it's in two variables, it's in whole plane. And so x-axis and y-axis. So so I mean at a comma b, it takes value. So f of a. So maybe you think of it as fx comma y. So f of a comma b, it's just a. And if I consider another function fxy, gxy, to be x squared plus x plus y squared minus 1. Now, of course, gxy and fxy are in the same equivalence class, because if you take their difference, you land in this ideal x squared plus is precisely x squared plus y squared minus 1. Yeah. And what is GAB? GAB is some complicated number. Yeah. So a squared plus a plus b squared minus 1. Yeah. So of course, these two functions are different. If you are looking at this function on the whole plane, xy plane. Yeah. But if you are looking at only on the circle, yeah, so you can of course restrict this function only on the circle x squared plus y squared equals 1. So restrict. So f restricted to let's call this C. Yeah, so or let's call this D for domain. Yeah, so f restricted to D again is A of a comma b is again A. But this is also equal to G and G restricted to D at some AB, where AB is in X. So restricted to D means we have to take AB in D. Yeah, so if you take AB in D, then a square plus b square is 1. Yeah, a square plus b square minus 1 is 0. So you again get it. So the rings contains functions which are sort of so there is no way to distinguish between f and g if you are restricting your domain to D. So this is the class of functions you should think about when you're trying to study the circle. Yeah. But the rings is not just about functions. You can also determine the so the ring also determines the picture as well. Yeah. So how do you determine the picture? So okay, so you want to know what are the points in this picture. Yeah, so that again you have to do some ideals. So you know what maximal ideal. So I suppose so I've taught BMath third year. So you know algebra 3. Yeah, so you know what maximal ideals and prime ideals are. So even if you don't remember, don't worry too much about it. I'll do a review if needed. Yeah. So what's an example of an ideal in Rx? A maximal ideal in Rxy. So there are many maximal ideal, but some nice maximal ideal I want to know in this ring. Yeah. So if I want to find a maximal ideal in this ring, then from your abstract algebra course, you should know, you may recall that it's same as max. So you find a maximal ideal, in Rxy containing x square plus y square minus 1. Yeah. So that is so maximal ideals of this ring is in fact in one-to-one bijection with. So maybe so I'll write a more reasonable set of notes once we start the course in a more reasonable way. Yeah. So what's an example of such a maximal ideal? Maximal ideals in so this is somewhat esoteric, but right hand side is somewhat more concrete. So what's some example of a maximal ideal of Rxy, which will certainly contain x square plus y square minus 1? Okay, so there are many chats.
Yeah, ideal generated by x and y minus 1, for example.
Yeah, ideal generated by x. Okay, so okay, so I missed a lot of comments. So feel free to interrupt me. Yeah, I don't see the chats while I'm lecturing. Yeah, and if you tell me, I'm sure this you guys can discuss among yourself as well. But if you have some questions, just speak it out. Yeah. So as someone asked whether this probably this part of the elliptic curve is smooth or not. So it is indeed smooth. Yeah. Yeah. So it's okay. Okay. So as one of you pointed out, so one of the disadvantages of online classes is I don't know who is speaking. While I'm talking, the whole screen, so I only see what you can call it as a blackboard, and I don't see you guys. So, and that's why I missed the chat as well. Okay. So if there's some interesting discussion going on, someone can just point me to it. Okay. Okay, so one of the examples, so I am not going to do the classification here. So some examples are, you can take x minus 1 and y, yeah, the ideal generated by x minus 1 comma y, or x comma y minus 1, or more generally, if so, these are some examples of maximal ideas in Rxy, such that it contains x square plus y square minus 1, or more generally. So maybe first let me say why this is the case. So you think about it, x minus 1 comma y. So the ideal generate. So this of course is a maximal ideal, because you go mod x minus 1 comma y, then you get r. Yeah, so this is indeed a maximal ideal. But why does it contain x square plus y square minus 1? So when you go mod this, you get r, which is a field. Yeah, so maybe you can in the chat you can say whether you are familiar with prime ideals. If you are not familiar with prime ideals or maximal ideals, just PM me. Yeah, and I'll do a short review. And so it's not difficult. I mean, since I just start, so one of the advantages of doing online classes is I can just move to this Algebra-3 and go to that notes and teach you from there. Yeah. So, yeah, so x minus 1 comma y contains this. Why? Because x square plus y square minus 1, you can think of it as okay, x minus 1 times x plus 1. So that's x square minus 1 plus y square. Yeah. So of course, the first term is a linear combination of x minus, is a multiple of x minus 1. Second term is a multiple of y. And similarly, this guy. Or more generally, if you have a and b are real numbers, such that a square plus b square equals 1, then x minus a comma y minus b so first of all, this is a maximal ideal, because if you go mod this, then also you get that the quotient is real numbers. So this is a maximal ideal of Rxy, and it contains x square plus y square minus 1. Since you just take x minus a times x plus a, and plus y minus b times y plus b. And if you think about it, this is equal to x square minus a square plus y square minus b square. But a square plus b square is 1, so this is x square plus y square minus 1. Okay, so this belongs to so that tells us that this whole guy belongs to this, and hence this guy belongs to x square minus y square, x square plus y square minus 1 belongs there. Okay, so these are so every point in some sense of this picture, you can get it via this. Yeah, and no other point. So in fact, a comma b in R be such that x minus a. So it classifies as well, is what I'm trying to say. X minus a comma x minus b contains x square plus y square minus 1 implies a square plus b square equals 1. Okay, so this also you can show. So the point is, if a comma b is such that a square plus b square is not equal to 1, then this x square plus y square minus 1 won't belong to the ideal x minus a comma x minus b. Okay, so this may be a little more work, but you can do this. Okay, so so this is how you can capture the geometry as well, using by just studying ideals in this ring. So the ring contains essentially all the information about the geometric side as well. Okay. Of course, you could also look at graph of some other functions like, okay, so maybe I can just write it here. So some other functions like which you may have seen in, or which people may study in y equals sine x, for instance. But I mean, this, of course, some geometers study that, but not algebraic geometers. Yeah? So the picture here looks like this, but we won't study this. Yeah. so not algebra geometric object. Because sin x is not really an algebraic object, yeah, it's a trigonometric object. So we won't study this picture exclusively in some sense. So any questions so far?
Will you write the statement of this correspondence? I mean, that the coordinate ring captures the geometry of the curve, or the variety really.
Yeah, so basically yeah, so what will be the statement? Yeah, so M spec, yeah, so basically the maximal set of maximal ideals of this ring Rxy modulo whatever the equation you have gone. Those set of maximal ideals is in some natural bijection with points on the locus of the equation. Yeah, that will be the, so natural bijection is so here there is some naturality. Yeah, so to make this rigorous, it will be so yeah. So there is some natural bijection. Yeah, so maybe I'll just so one has to bring in some topology, etc., to make this more rigorous. But there is a bijection between real points of it and points which satisfy this equation and set of all maximal ideals of this ring.
We have done the Zariski topology in ring theory.
Set of maximal.
So you can.
So set of maximal ideals of a particular kind. Yeah, and, so there may be some other maximal ideals. So, yeah. So you were saying something. You have done something.
Yeah, we have done Zariski topology in ring theory 3, so you can use that. You don't have to say what.
I see. So you have done some Zariski topology. Yeah, so, but still, how do I? Yeah, so it's not just, yeah, so maybe I'll state it this way, yeah, so maybe without even, so maybe, so proposition, so since I'm trying to make, so maybe I'll make a statement over C so that I don't make any mistake, yeah, and but the proof is a bit, it goes via Hilbert-Nullstellensatz, so maybe so let me, yeah, so maybe let me try to make it over C, and maybe I'll make a somewhat weaker statement so that one doesn't need anything, yeah. So let in CXY, let F be a polynomial and be an element, then the locus of so yeah, so I can just rewrite this statement. Yeah, so then A comma B in C2 is in the locus of F if and only if f belongs to x minus a or y minus b. The maximum if only if f belongs to this. Yeah, so then I don't need C. I can put R or any field. Yeah. So maximal ideals of this kind, so to speak, belongs to X. So I can so here yeah. So this is the statement, if you like. Okay. So this is the picture. Let's start. So this, of course, you can once we talk about zero set, etc. This will not be restricted to just one polynomial, but maybe more than one polynomial, and so on. Okay. Yeah. So once so you can make out this. So basically, using the maximal ideals, you can make out this whole picture. So the nearness, the notion of nearness, etc., continuity, etc., those requires more. So we can think about some topology on this thing because it's an object. There is some sort of topology. So those things will require some Zariski topology, etc., some continuity, etc. So all that you can give some topology on set of maximal ideals or prime ideals on this, and the topology which sort of maybe some topology which you can think of on this R2 and restrict it, and those bijections also hold. But let's not worry about it right now. Okay. So right now, let's just give a bijection like this. Okay, so this is yeah. So we'll talk more about. So we'll start. I will discuss this zero set, etc. more later. But in this, so mostly what I'll do is so in my notes, what I say is I've said that. So I'm not going to follow some book rigorously, but books you can refer to is something like undergraduate. So for graduate algebraic geometry by Miles Reed. Okay, it's frozen. By Miles Reed, REID, and then he also has an undergraduate commutative algebra, so by the same guy. So you can look for commutative algebra part, you can look there as well, but there is a big overlap. Yeah, so I mean, I'm not suggesting you buy any of these books. Yeah, most of them you can probably find somewhere. Yeah, and then of course for commutative algebra, you can also look at Atya MacDonald or so commutative algebra. Or maybe it's called Introduction to Commutative Algebra. Atya MacDonald. TIAH, not TIO. And there is one, I mean, it's a fat book, but this is basically, I mean, this is how I am treating this course, commutative algebra with a view towards algebraic geometry. so this is by Eisenberg. So, I mean, of course, we are not going to cover the book. It's like a, but you know, there are some things I may pick out from there. And then for algebraic geometry part, apart from my street, there is basic algebraic geometry by Shafrovich. So this is also not very advanced, so one can look at this, yeah, and so on. So there are, I mean, these are some of the more popular. So these days I hear there are many other popular undergraduate books, but these are the ones I've looked at while teaching this undergraduate course. Okay. So maybe what I can say is that yeah. So Zariski part I'll repeat. So whatever is not part of the syllabus I'll do. Yeah. So I'll talk about these sets, zero set and stuff, because that's one of the topics. I mean, if some of you are advanced, I don't know, maybe you can, there are courses in math, algebraic geometry one can take and learn that. So I'm not going to make this advanced, yeah. This is going to be a basic course. But let me tell you, so whatever I say in the next 10 minutes may not make sense much, but I just want to tell you what the picture is as far as curves are there, yeah. So as I said, people want to classify geometric objects, yeah. So one of the goal is to classify these geometric objects. So you know, there is a so from the picture you can see that these are curves, yeah. Of course, if I tell you take a picture like x square, so if I tell you I look at the graph of this guy, of course in 3 space, then this is not a curve, right? You can make out it's a surface. So without even getting into what rigorously what the definition of dimension is, roughly you know what the definition of dimension is. Yeah. So without saying what curves are, so it's a one-dimensional object. Yeah. Whatever that means. So people have classified curves. So the two examples I gave you are so one is part of P1 and the other is part of elliptic curve. So they have classified curve, meaning somehow if you think of projective curves, then they are proper curves, then they have classified it, in more or less complete generality. But over complex numbers, yeah, so it's yeah, so affine curves are still difficult, so you have to understand automorphisms and so on, so to say whether two curves are affine curves or isomorphic. So that's still I don't know what the picture is, yeah. So for some affine curve, so for some so I'll tell you the picture in the projective case, and I'll tell you why it is more easier in projective case and more complicated in non-projective case, so to speak. So I gave you this example: x square plus y square equals 1. Okay. So this is a circle, and then there is an example x square equals y, which is a parabola. Yeah. And then there is x square plus y square, 2x square plus y square equals 1. So this is some sort of an ellipse. Yeah, and then there's x square minus y square equals 1, which is hyperbola. So these all three guys give you different picture if you are looking over reals. And they all look different. I mean, so somehow 2x square plus y square equals 1 and x square plus y square equals 1 look pretty similar. I mean, ellipse and circle, you just stretch a little bit. So when you classify in rings as well, I mean, you classify up to isomorphism, yeah? So in some sense, these are isomorphic in over R as well, but the others are quite different, yeah? So they look different. These are sort of same. But once you move to complex numbers, but over C, even this one looks the same. Yeah, so all these three are same over complex numbers. Okay, so you can show that they are these three pictures will give you more or less the same thing. So it's difficult to visualize over C, unfortunately. But they all become somewhat similar equations. Yeah. So the reason there was a problem is there is no square root of -1 in R, but that problem vanishes when you are over complex numbers. Okay. So they all look similar. So one can say, so more rigorously, if you want to say, then I'll say that the rings corresponding to this. So CXY. Okay. So CXY modulo whichever these three things you get, x square minus 1, x square, so maybe I'll write F1, F2, F3. So mod F1, CXY mod F2. So one way of saying that they are same. So once we talk about varieties, and then I can say in terms of geometry as well, but right now we don't have geometry. So these three rings you can show are isomorphic. Okay, and the F and this first one, even if you replace R by C by R, then also is isomorphic. But this fourth one is not isomorphic. Yeah. So there is something called projective geometry, which we'll talk about later. So they are like compact objects. So I mean, these pictures are not compact. This circle looks compact, but once you go to complex numbers, it won't look compact. Yeah. But if you think of compact curves, let's say, then all these four becomes isomorphic. So you do a compactification of all these four objects, then they all become isomorphic, and it's P1. Okay. So it's a curve and curve P1, and they are all isomorphic. And so there's but it's not isomorphic to the second example. So the second example, if you compactify it, what you get is elliptic curve. Yeah, elliptic curve. So how does the picture of P1C looks like? So this is same. So this is basically compactifying C, 1-point compactification of C. And this we talked about in topology course. Yeah, so it looks like a sphere. And this is how P1C looks like. And how does an elliptic curve look like? It's like a donut. So you may have heard that many times. So so even topologically, they are not same. Yeah, so you can distinguish them in some way. So they are not isomorphic. So what people have done in algebraic geometry curves, they have classified in the following sense. So they have developed an invariant, which is called genus. So any genus zero curve over C, compact genus zero curve over C is going to be isomorphic to P1C. Now, if the genus is 1, then it's going to look like elliptic curve. So it's going to look like a donut, and it's called an elliptic curve. And there are many of them. Yeah. So there is a family, one-dimensional family is parameterized by, let's say, C. Yeah. So there is a one-dimensional family of elliptic curves parameterized by C. And then there are higher genus curve. So for each genus, higher genus meaning, so genus 2 onwards. So the picture is going to look like, okay, maybe. So if there are G genus, then there will be G holes like this. Okay. And so topologically, the picture will look like this. And genus G. And there are many, so like an elliptic curve, there are infinitely many elliptic curves up to isomorphism as well. So so genus 0 is special. There's only one guy. Okay, everything. But in elliptic curve, there are infinitely many. Here also there are infinitely many, and so you can one can parameterize it. So, but now the moduli is slightly more complicated. So the parameterizing family is parameterized by not just one-dimensional. So here it was then parameterized by one-dimensional object, C. Yeah, C is like one-dimensional, one complex dimension, let's say. Yeah. So similarly, this so if genus G is greater or equal to, then it is 3G minus 3-dimensional object parameterizes all genus G curves. Okay, genus G, yeah. So compact curves. So people have studied this so curves in some sense is fairly well understood. Yeah. Projective curves is fairly well understood. Over complex numbers is even better understood. Okay, so so there is a whole so over complex numbers there is a whole subject dedicated to it, and it's also called Riemann surfaces, because for algebraic geometry it is a curve, but of course others think it's a surface. Yeah. So it's a so Riemann surfaces are precisely about these things, and they are so they are algebraic curves and Riemann surfaces are more or less the same thing. Okay. Okay, there is. Okay, so maybe this is a good place to stop. So so I'll stop here today, and next time I'll start a more reasonable discussion. So there is something about some chats were there, but I think maybe Karthik had some question, but hopefully I think Balarka sort of. So maybe you were trying to do the other direction. Yeah. So if x square plus y square if A and B are such that A square plus B square is not equal to 1, then you want to show that x square plus y square, and then you want to show that x square plus y square minus 1 does not belong there. Yeah. So the point, yeah. So you can write an identity. So the point is x minus a and y minus b is this forms a maximal ideal. So okay. So you can think about it. Yeah, I think this is not too bad. Yeah, so I mean, you just take the linear combination, x minus a times x plus a plus y minus b times y plus b. This is going to be x square plus, so this is x square. So I think you can use the same thing, minus a square minus b square. And of course, a square plus b square is some r, which is different from 1. Then this becomes x square plus y square minus r. And this, of course, can't contain x square plus y square minus 1 as well if r is different from 1, because then it will contain r minus 1, which is a unit. Yeah. So that is the argument you can use. Okay. So maybe we'll stop here today. And but before leaving, maybe you can tell me. So prime ideals, maximal ideals. So you can tell me if I can assume these things. Yeah, notion of prime ideals, maximal ideals, UFDs, yeah, and and the prime ideal P is a prime ideal if and only if R mod P is an integral domain. So maybe I'll state these results next time on a piece of paper, and if you need some justification, then we'll go over it slowly. But if these things seem familiar, then okay. So those things are fairly covered. Okay. So maybe I'll skip through some of this. Yeah, and maybe I'll do some review of nilpotence and radical ideal reduced string and so on, radical of an ideal and so on. So maybe I'll move towards that direction. Okay, and as usual, there will be some homeworks assigned, and so every week I'll put up some homework, and you're expected to do this and turn in. There will be So a lot of grade will depend upon homework, and then some of it will depend upon the final. Okay. Okay, so that's it for today. Let me stop the recording.